All right, so today we are calculating probabilities of compound events. Now, compound events means more than one. All right, so we've got more than one thing that's going on. So it's not just this or this; it's this and this and this. So that's the part they're focusing in on today. There. So one of the techniques here is, and the previous diagram talks about tree diagram. We're going to see the tree diagrams for the first time today. All the tree diagram does is it organizes the outcomes of what can happen. This way we don't lose anyone. So it's not just randomly guessing, well, this could happen, this could happen, this could happen. It's a systematic way of making sure we get all of the different outcomes that could happen. So we're talking about a game here, and they're talking about on a family that wants to play either a board game or a card game. So what they're saying is, hey, on Monday, you could play a board game or you could play a card game. Well, on Monday, if we play the board game, and then on Tuesday, well, you could play the board game or the card game, which meant your outcomes could be board game, or board game, card game. And then let's say, whoa, let's play cards on Monday. Then you still have the outcome of playing the board game then on Tuesday or the card game. So again, it lists out all the possible examples. The tree diagram, again, talk tree because we just have branches that go along with it. So let's see what we got here. All right. Now what they've done here is, oh my goodness, we've added a third day onto it. Okay, so again, the whole idea is you could do board game on Monday, and again, you can see how it's kind of lined up there if you'd like to kind of separate things. And then on Tuesday, again, board game, card game. And then on Wednesday, board game, card game. So the main thing is off of each branch, we get the different possibilities that we've got. So we could go board game, board game, board game. We could go board game, card game. Okay, we could go board game, card game, board game. There we go, board game, card. So again, we're just listing them all so we get them all there. So what we're asking us here is if BBB represents 3 straight nights of board games, what does CBB represent? Well, C represents a card game, all right, followed by a board game, followed by a board game. Again, so we're just, ooh, that's bad, all right. We're just going about the table and reading the information that's there. So list all outcomes where exactly 2 board games were played over 3 days. So list 2 outcomes where exactly 2 board games were played. So 2 board games means we need 2 letter B's in there. So we could have board game, card game, and we could see that guy right there. We can also see this guy as well, board game, card game, board game, because again, there were exactly 2 board games. No, oh yes, so card game, board game, no, we don't have 2 board games. No, we don't have 2, no. So yeah, we had 3 of them there. So again, it's listing them all out and then reading what your results are. So it says there are 8 possible outcomes representing the 3 nights, and there's your 8 of them that we've got right there. Are the 8 outcomes representing the 3 nights equally likely? Why or why not? Well, this is where we're going to get into the fact of yes, they are. And now equally likely. Why? Because how many choices were there? Well, there were 2 choices, all right, which means they all had the same, all right, probability, all right. Everything that we are looking at had the probability of 1/2 because we could have board game or card game. Board game, everything's a half there. So because they were all the exact same, that's why all of these outcomes are going to end up being equal. If you would like to, as we kind of label it there, is we could label it this is a half that's there, and you could see for the board game it would be a half. The card game would happen to be half. And no matter where we put it there, there's always 2 choices, and it was always one out of the 2 particular choices. So what we're after here now is actually calculating the probability that's here. So again, the tree diagram, as we saw before, put everything out in order for all the possibilities. But what they're saying here is, all right, listen, all right, we're going to tell you that based on the number, there's a 75% chance that we're going to play the board game. And there's only a 25% chance that we're going to play cards. All right, so again, now we're saying that it's not equal. And again, we can base this off of the people because of the people that are agreeing to play it. So it says probabilities for 2 of the 8 outcomes are known. And the idea here is it's the word and. All right, and means that you are going to have to multiply. All right, so that's a big thing that we wanted. So and means multiply, whereas before we saw or that's the one that means that you are going to add. So that's the key kind of phrase here. So probabilities for 2 to the 8. I'm going to calculate the approximate probabilities for the remaining 6 outcomes. All right. So if we want board game, card game, well, the probability of doing board game, card game. The probability of a board game, 7,500s. And then another board game, well, that's 7,500s. And then another card game, well, that is 2,500s. So this is where we reach for our calculator. All right, go and reach for it there. We punch it all in, and you end up with decimal 1,4,0,6,2,5. But we're always going to round to the nearest percent. So we can times it by 100, move it 2 spaces to the right, however you would like to say it, and you would get 14%. So there would be a 14% chance of doing a board game, and then a card game there. All right. What we want you to notice is that for the board game, card game, I'm looking at the second one that's there. It too will have a 14% because we're still multiplying all the same 3 numbers that are together. So it is still going to give us the exact same result. What we do want to look at is someone that's like this. And we're not going to do all of them because it's just multiplying them out. But if I do board game, card game, what's the probability of board game happening? Well, they told us that it's a 75% chance, so 7,500s. What's the probability of a card game? Well, that's 25% chance, so 2,500s. And again, another card game is your 2,500. So if we multiply those numbers together, you get 0.046875. Change it to a percent, and if we round it to the nearest percent, you're going to get 5%. Now, this is what we want you to watch for, is, oh my goodness, but there's 3 of them here, but they're not the same. Well, right, because we're trying to get the card games to happen, and there's a smaller chance that the card game's actually going to end up happening. So that's why, all right, it's going to be a little bit lower in that particular time. All right, so we do need to watch for that. So let's stop there. I know I said fill them all in, but we don't need to. So what's the probability that it will be exactly 2 nights of board games over the 3 nights? Exactly 2 nights of board games. So let's find where we have exactly 2 nights of board games. All right. That's 3. Oh, there's 2. All right, so it's B, a C. All right. Ooh, there's 2. Board game, card game, board game. Exactly 2 nights of board games. No. Ooh, there's another one. Card game, board game. And then no. Now, if we look at this, no matter what we do percentage-wise, the 2 games, the board games, we're going to get that 14%. Now, how do I know that? Well, we did it right up here. We're always going to be multiplying the same numbers together, which is why I'm going to get a 14% every single time as we look at it. So what's the probability that there will be exactly 2 nights of board games over the 3 particular nights that we are looking at? So we want to know this could happen, or this could happen, or this could happen. As we talk about, the word or means that we're going to add. So 14% plus 14% plus 14%. We'll add those all up together, and you should end up getting 42%. So there's a 42% chance that we're going to get exactly 2 nights of board games. Now, again, this is the part we got to watch for. I want this to happen, and this, and this. That's why we're multiplying to get to our 14%. But I'm asking for this could happen, or this could happen, or this could happen, which is why we will end up adding them together. All right. What's the probability that a family will play at least 1 night of card games? At least 1 night of card games. Well, how many nights of card games are there? Well, there's at least 1, a 2, a 3, a 4, a 5. That's card. There's only 1 that's one right there. So the idea behind this is instead of adding them all up, all right, we can actually ask the opposite question, and what's the probability of not playing cards, and we can subtract the 1. And that's what we saw in the previous lesson. So we could add them all up, that's fine, or we could just do 1 minus, and we can see here the probability of that happening is 42%. So there's your 42 hundredths. So we could just do our subtraction problem and get 58 hundredths, which is 58%. So again, instead of adding them all up, we could just do the subtraction problem of what we're looking at. So let's look at the next one that we've got. 75% chance of happening. This had a 25% chance of happening. So we did have different probabilities. And you can see when we did our multiplication, we used different numbers. Now down here, as we go through it, we're talking about having, we're talking about the kids that could happen there. So we have 3 children that we are dealing with there. So we've got our first child, all right, we've got our second child, and we've got our third child. So with our first child, we could have a possibility of a boy or it could be a girl. When we list them out there, that after the second child, well, we could have a boy, and again, we could have a girl. If the first child was a girl, it could be a boy, and then it could be a girl. After the second child is born, again, your options, you could be a boy or it could be a girl. And again, if it was a girl, it could have been a boy, it could have been a girl. You kind of see what we've got going on here wise, all right, regarding our tree diagram. So if we list out all the possible outcomes, it could be boy, boy, boy. And again, we're going right across the line. It could be boy, boy, girl. So boy, boy, and then a girl. And then boy, girl, boy. So boy, girl, boy. And then boy, girl, and then a girl. All right, and so now we're going to have another set of 8 outcomes, if we, no, sorry, 4 outcomes if we start with just the girl. So it could be girl, boy, and a boy. It could be a girl, a boy, and then a girl. And again, we're just going through, pulling off the trees and the branches here. And then we could have a girl, and then a girl, and then a boy, and then a girl, and then another girl that we're looking at. So when we write in the probabilities of each stage outcomes, the probability for all of them is going to be a half. All right, because there's only 2 options. It could be a boy, it could be a girl, and that's what we're left with. So we're going to have halves absolutely everywhere. So we're not going to fill them in all over the place, but that's the whole idea behind it. So now they want you to figure out the probabilities. Well, it's always a half. So no matter what you do, it's going to be a half times a half times a half. Because again, the probability of getting the first shot and then multiplication. So when we look at that, we're just going to multiply the halves together, which would give us 1/8. We can change that into our decimal, and then we can round to the nearest percent everything. So it's about 13% chance. And it's going to be for all of them, all right, because the probabilities don't change from one to the other. So they want to know what's the probability of having 3 girls in this situation. Well, the only way you can have 3 girls in this situation is to have girl, girl, girl. All right, and we know that that is 0.125. All right, which is about your 13%. Now, is that greater than or is it less than the probability of having exactly 2 girls? So exactly 2 girls. So how many places have exactly 2 girls? Well, no, 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 boy, girl, girl. 2 girls, no, girl, boy, girl. And then, girl, girl, and then a boy. So each of those we knew were 0.125. And the idea here is we could have this or this or this. So we should be adding them up together. So 0.375. So we're looking at about 38% that we are after. So again, we multiply to find the individual probabilities, but then we add because this could happen or this could happen or this could end up happening. So when we look at the very last problem that we've got there, what's the probability of a family of children having at least one girl? At least one girl, all right? So in other words, we're asking them to have not all three boys. So this is where it's going to speed things up. I can simply do 1 minus 0.125. All right, so I can do 1 minus because it's the not, and there I get 0.875, so we're looking at about our 88% chance of that happening. All right. So that's the part we want to make sure that we're kind of clear on. That's the part we're going to be working on in class a few more times more, is making the tree diagrams and then being able to break it down. Again, if we want repetitive things to happen, it's a multiplication problem. I want this and this and this. If it's an or, well, I don't care. Or this, or means that's why we are going to add them all up together.